And then you might ask, okay, well, we saw how we can represent the probability distribution over a single variable. Like, what if we have more than one variables in the environment? Well, then we use something called a joint distribution. So a joint distribution is going to be a probability table over a set of random variables. In this case, x1 all the way to xn, and we'll assign a number to each, of all possible combinations for all n variables. So we can in the shorthand we can write each of the rows will be represented by a probability of lowercase x1, x2, all the way to xn.
And each of these is a number, basically.
Yeah. So here's an example for the joint distribution for temperature and weather. And joint distribution also need to satisfy two key properties. The first thing is, all the rows must have entries greater than or equal to 0, and all the rows must sum to the value of 1. So, Carl, what do you think? What should be the size of distribution if I have n variables and each with domain size d?
So by the rule of counting, if each variable can take on value d, for n variable, it would be d to the n.
Yeah.
So in this example, since you have two variables, each have a domain size of 2, then it will be 2 to the 2.
Right.
And since you brought it up, this is actually exponential to the number of to the domain sizes. So it is usually impractical to write out explicitly the joint distribution, the big table. And that's why in future lectures, we'll talk about how to model the big table with simpler and more concise, smaller tables. But that's just the basic stuff first.
Yeah, so in the next part, we're going to talk about, the preliminary definitions for probabilistic models. So a probabilistic model is just a joint distribution over a set of random variables. So the probabilistic models for temperature and weather will be indicated by the joint probability distribution as you saw in the middle of the slide here. There's few key components, for each probabilistic model: the random variables, the assignments, which are called outcomes, and the joint distributions, which basically are the tables, and it indicates how likely is each of the assignments. The probabilistic model needs to be normalized, which means all entries sums to 1, and ideally it's only over the set of variables that interact with each other. So this, is related to some properties like independence, which we will talk about later in this course.
Okay, let's talk about events. An event is basically a set of outcomes, and the probability of that event is the summation of the probabilities of all the outcomes that constitute that event. So let's go over an example. And you know that from a joint distribution, we can calculate the probability of any event, because the joint distribution offers us a very powerful way to model the probabilities. So for example, if we have the joint distribution of the temperature and the weather here, and we try to calculate the event that it is hot and sunny, we will just pick the assignment that corresponds to the temperature being hot and the weather being sunny, which is essentially this assignment. And since that's the only assignment that satisfies this event, it would just be 0.4 here. So if the event is just hot, there are actually 2 rows that satisfy this event, which means we would have to add up 0.4 and 0.1. And the probability of that event would be 0.5. And last but not the least, if it is hot or sunny, which means we could pick these two rows with the third row because it is sunny. So we would add up 0.4, add 0.1, add 0.2, and we'll get 0.7. So, and that's how you calculate the probability of an event using a joint distribution. So typically, the events we care about are partial assignments and not the full probability table. And that's why, these calculations are needed.
So the next part, we would like to look at marginal distributions. So marginal distributions are subtables where we eliminate some of the irrelevant variables. So marginalization, which is the process of summing out irrelevant variables, is basically combining and collapse rows by adding the rows correspond to the irrelevant variables. So let's say we have a probability table, a joint probability table for temperature and weather. So let's say we only care about the probability for temperature. What we will do is we will sum over all possible values for the weather variables. So let's say we want to calculate probability of hot, we'll sum over probability of hot, sunny, and hot, rainy. So that's how we will get 0.5 as the first entry, and similarly we can do that for the code. On the other hand, if we don't care about the temperature and we're only concerned about the weather, we'll sum out the temperature variable basically the same way.
So this is a more general case of how do we marginalize over certain variables just by summing them out.
So in the next part, we'd like to talk about conditional probabilities. So probability of A given B is actually the probability of the joint distributions between A and B divided by probability of B. And if you want to look at a specific example, let's use the temperature and the weather table from before.
Oh yeah, so I'll go over the example. So for example, if we're interested in the probability of weather being sunny given that the temperature is cold, so follow that formula, we will compute P of S and C divided by P of C. That's just a shorthand. So we can find P of S and C in the table here. So this is 0.2. And on the other hand, for P of C, remember we used marginalization to calculate P of C. So P of cold is just summing out these two rows. So 0.2 plus 0.3, and this will be 0.4. So let me just clear out my drawing here. And note that another interpretation for the conditional probabilities is denoted in the Venn diagram. So the joint, you can think of it as the intersection of the two regions. And the conditional probability is essentially the area of this intersection divided by the area of the circle corresponding to the probability distribution of B. Okay, so since we know how to calculate conditional probabilities, conditional distributions are just a table filled with conditional probabilities. So for example, if we were to calculate this row, we would follow the procedure of calculating PW equals to S given T equals to H. And that's introduced in the previous slide. And if we wanted to calculate this row, we will still fix T equals to hot and just calculate W equals to R given T equals to hot. So I won't go over the calculations because you can find them in the previous slide. And similarly, if we want to fix T equals to cold, the other conditional distribution on W would be calculated similarly. And these two little tables combined is the conditional distribution of W given T. So you can see this neat comparison between the conditional distribution and the joint distribution.
So one way to calculate entries in the conditional probability table is by carrying out the whole calculations like Carl did in the previous slides. But there's a trick that we can apply, which is basically just select the joint probability, the rows in the joint probability distribution that's consistent with the evidence. So in this case, since we know the temperature is cold, we only select the last two rows. And then we basically just perform the normalization by, scaling the two entries such that they add up to 1. And that's actually how we will be able to get the conditional probability distributions for, the weather variable given that the temperature is cold. So you might ask, why does this work? Well, it's because, the sum of the rows that's consistent with the evidence variable is basically the probability for the evidence. In this case, that will be the probability of temperature equals to cold.
Great. So what does it mean to normalize? And from the dictionary definition, to normalize just means to bring or restore a normal condition. And what is the normal condition in the probability distribution? It means that all the entries in the probability distribution sum up to 1. And so, like Masoud said, the normalization trick is essentially computing a z, and that z equals to the sum over all the entries. And eventually, you would divide every entry by z. So for example, in the last example, z would be 0.5 because 0.2 plus 0.3 is the sum over all entries. And 0.4 is actually calculated by using 0.2 divided by z, which is 0.4. So the second example, imagine that this p doesn't represent a probability, but instead some other values. And similarly, we can normalize it in the way that a probability distribution requires.